The idea here is if you've got some object that's moving around, we want to be able to keep track of its position, its velocity, and its acceleration at all times. And usually the most convenient way to do this is with three graphs. So we're going to have a graph of position versus time. And this might be labeled X or Y, or maybe even something else, depending on, are we talking about horizontal motion or vertical motion? Either way, we're going to put it on the dependent variable axis, the vertical axis. But this might be labeled X or Y or even something else. It's just the distance traveled or where the object is. And then a graph of velocity versus time. And a graph of acceleration versus time. And typically we're assuming the object is moving only in one dimension. It's moving only horizontally or only vertically or only along a straight line. If it's moving in two dimensions, typically you'd set up two sets of graphs. X, v sub x, a sub x, and then y, v sub y, a sub y, keeping track of its x and y components of all of these variables. Also, I find it's usually a good idea to stack these graphs vertically like this, because that way, since they all have the same time axis, if something important happens at a certain instant in time, let's say t sub 1, if you stack these vertically, it becomes very easy to keep track of that same time on all three graphs. So arrange these in this sort of fashion, vertically, position, velocity, acceleration graphs. And that way it's very easy to compare what's going on at the same time on all three graphs. If you put them side by side, it's more difficult to see that. So that's our general setup: position graph, velocity graph, acceleration graph. How or where the object is, how fast the object is moving, and how fast its motion is changing. Any questions on that setup so far? So let's take a look at how these are related to each other. How do we define velocity in the first place? What is velocity?
The change in distance over time.
Right. Change in distance over change in time, which we should really be writing as a derivative. If we're talking about these as graphs, velocity is the derivative of position. dx over dt or dy over dt if you're talking about vertical motion, but it's the derivative of position with respect to time, how fast the position is changing. And what does that tell you about a graph? If you find the derivative of a function, what does that tell you about the graph of that function?
Its slope?
Yeah, this is literally just the slope of the position graph. Formally, the slope of the tangent line, because the curve doesn't really have a slope. But at any point on the curve, you can draw in a tangent line. The derivative tells you the slope of that tangent line. So the velocity, the value of velocity tells you the slope of position. For instance, if velocity is a positive value, then position has a positive slope. And the larger the velocity is, the steeper the position graph will be. So the value of velocity tells you the slope of position. And vice versa. If you know the slope of position, that tells you the value of velocity. In any region of time where the position is increasing, you know the velocity has to be positive in that time. What about the relationship between velocity and acceleration? How do we define acceleration in the first place? What is acceleration?
The change in velocity over time.
Right, which we could also write as a derivative, dv over dt. So in the same way that velocity is how fast the position is changing, likewise acceleration is how fast the velocity is changing, the derivative of velocity. And this tells us the same thing about the graph. The acceleration, the value of acceleration tells you the slope of the velocity graph. And you can interpret these analytically with calculus or geometrically with the shape of the graph. So the value of acceleration tells you the slope of the velocity graph. Or alternatively, if you have a function for velocity, you could just take the derivative of that function and get a function for acceleration. Any questions on those so far? So let's try out an example. Let's say we have a graph for position. Maybe we have an object that is, let's say, starting off at position 0, and then it travels in the positive x direction for a while, and then it turns around and travels in the negative x direction for a while, and then turns around and travels in the positive direction for a while. So there's our hypothetical graph of position. And you could get this graph, maybe you're just watching the object and writing down where it is at every instant. Or maybe you've got a video and you're playing it frame by frame. And each instant you can measure where the object is and write that down on a graph. If you have that position graph, you can then use that to draw a velocity graph, and then use the velocity graph to draw the acceleration graph. And to do that, we want to split this up based on what times its velocity, its slope has certain values. For instance, if you take a look at the first amount of time here, maybe from here to here, from this instant to this instant, what can you say about the slope during that period of time?
It's positive.
Yeah, slope is positive. So during this period of time, the velocity has to have a positive value. Position having a positive slope means velocity has to have a positive value. Also, it looks like this is a fairly constant slope. During this period of time, the position graph looks like a straight line. If the position graph has constant slope, we can assume the velocity graph has a constant value. So if the position graph has constant positive slope during that period of time, we would assume the velocity graph has a constant positive value during that period of time. If we take a look at the next little period of time here, though, we actually have a very important thing going on at this maximum. Position has reached a maximum. At that instant, when position reaches a maximum, what is its slope?
Zero.
Got to be 0, right? And this goes back to the idea from calculus. If you're looking for the maximum value of a function, if you've got some function that has reached a max or a min, at that instant when it's at its maximum, the slope is 0. At the instant when it's at its minimum, the slope is 0. So maxes and mins are very important things to look for here. If you've got some curving function that reaches a maximum height or a minimum height, at those instants, the slope has to be 0. So that's actually a good thing to look for. Before you even start everything else, if you've got a position graph, look for any instance in time where it hits a max or a min. At those instants, the velocity has to be 0. So we know our velocity graph has to go through those 2 points. Anytime you know that the position graph hits a max or a min at that instant, the velocity graph has to be 0, and the velocity has to have value 0, because the slope at a max or a min is 0. And that splits this up nicely into when it's positive and when it's negative. The location or the times when we have 0 slope on the position graph and therefore 0 velocity split this up into regions of time when velocity is positive versus regions of time when velocity is negative. For example, in this entire region, the slope of position is positive, so the value of velocity has to be positive. In this entire region, the position's decreasing, that's a negative slope, so we have to have a negative velocity. Some more space there. And then in this entire region, the position is an increasing function. Position has positive slope, so the velocity is going to be positive. What does it mean to have a negative velocity? For velocity, positive and negative is all about direction. So if we define some direction to be positive, a positive velocity means the object is moving in that direction. A negative velocity means the object is moving in the opposite direction. And formally, since velocity is a vector, it doesn't really have a positive or negative sign. It just has a magnitude and a direction. But if we're talking about a one-dimensional motion just along a single straight line, then you can treat one direction as being called positive and the other direction as being called negative. Or if it works better, you can think of this graph as representing just not the actual velocity vector, but just the x component of velocity. We can even just label this as v sub x and a sub x. So positive velocity x component means the object is moving in the x direction. A negative value means it's moving in the opposite of the x direction. So we know we've got to have a positive velocity in this region, a negative velocity in this region. And in fact, if we ignore those little curvatures here, it looks like between this time and this time, the position graph is pretty much a straight line. So if the position graph is a straight line, what do you know about the slope of a straight line? If this truly is a straight line, if you measure the slope here and the slope here and the slope here, what would you expect about those slopes?
They're the same.
Yeah, they're all going to be the same. If this truly is a straight line, even for just a portion of time, then during that portion of time, the slope is constant. Slope of position being constant means the value of velocity is constant. So velocity is during that period of time, let's say from here to here, the velocity is going to be some negative constant. Also, how do those slopes compare? What can you say about this negative slope versus this positive slope? Are those about the same magnitude or are they different? What would you say in describing the steepness?
They look pretty similar, but maybe the middle one is a little bit smaller.
Yeah, this one, they're almost the same, but this one does look a little bit
In
less. So if we have kind of steep and then a little bit less steep, that means this negative velocity is going to be smaller than this positive velocity. So instead of being this far below the axis, it'll be a little bit less below the axis, maybe here, let's say. But we can treat it as a constant value because during this period of time, the slope is the position slope is constant, which means the velocity's value is constant. But then afterwards, from here onwards, it looks like we're back to a positive slope and therefore a positive value for velocity. And it looks like this is about the same steepness as the original before. So back to this large positive. So our velocity graph is going to be a large constant positive, a weaker constant negative, and a strong constant positive again. Any questions on those sections so far? Then let's take a closer look at these corners, these in-between regions, because we've been kind of skipping over where it changes from a straight line to a curve, and then from a straight line to another curve. Those curves in between. this curve here, we know it's got we know the velocity has to pass through 0 velocity at the instant when the curve flattens out at the maximum and the minimum. But in between, this curvature means that the position graph is gradually changing from a positive slope, looping around to a negative slope. And then from a negative slope, curving around to a positive slope. That curvature means the velocity is gradually changing from one value to another. So in the in-between regions, we know during this short period of time, the velocity has to change from this positive value to 0 to this negative value. And we can probably assume that this is a straight line or close to a straight line. It might not truly be exactly a straight line, but for short periods of time, any curve is almost straight on a small scale. So we should connect these because generally you want to connect points on a graph if the in-between values actually have meaning. Like if we don't connect these, we're saying that there are instants in time where the object does not have velocity. Not that it has 0 velocity, but that its velocity doesn't exist. And that doesn't make sense. It should have a value for velocity at every instant in time. So we should expect a point at every time. We need to have this be truly a function. Every instant in time needs to be associated with a velocity. Likewise over here, it's not like it doesn't have a velocity during this period of time. It's that its velocity is changing from position having a negative slope to position having a 0 slope to position having a positive slope again. So we're going to have a gradual transition from negative velocity to 0 velocity to positive velocity. Something like that. And again, it's not necessarily exactly a straight line. We can't necessarily tell just from looking at the position graph exactly what that's going to be. But a straight line is at least a good approximation, a good first guess. So this would be our velocity graph then. It's going to be positive for a while the object is moving in the positive direction. Then the velocity transitions to 0, gets weaker and becomes 0 because the object has slowed down, come to a stop. The velocity becomes negative because the object is now moving in the backwards direction. Velocity stays negative for a while as the object continues to move in the backwards direction. And note that as the position graph crosses over 0, what would that represent? What does 0 position mean? Does 0 position have a meaning?
Does it just mean that they're back at the starting point?
In this case, yeah, because we were starting at x equals 0 in the first place. If you start at x equals 0 and then some amount of time later you're back at x equals 0, that means the object has returned to its starting position. And then continuing into the negative means it's now behind where it started. And you don't necessarily have to call the starting position 0. We could have set up our coordinate system however we wanted. You could call, maybe we put 0 down here and you call this x equals 100. But the important thing is it has returned to the starting value of x, regardless of whether we're calling that 0 or not. So that means that it has gone back to its starting point, keeps going, so it's now behind its starting point, then turns around again and goes forward to get back to its starting point. So that's the position graph. Velocity graph is describing what its speed is at any instant. It's going fast in the forward direction, then slows down, comes to a stop, starts going slowly in the backwards direction, slows down, comes to a stop, and starts going fast in the forwards direction again. And you could think of the velocity graph as what's shown on a speedometer. If you have let's say you're in a vehicle that has a speedometer showing how fast you're going, if you just watch that speedometer and write down what it shows at each instant, you can make the velocity graph. Any questions on that so far? And this is also reversible, by the way. In this case, we started with the position graph and we use that to draw the velocity graph. But in the other direction, if you have the velocity graph, you can use that to draw a position graph. Like if all you know is a velocity graph, maybe you were in a car with no windows, but you were able to watch the speedometer. Then if the velocity is positive, you draw a position graph with a positive slope. Velocity gets weaker and hits 0, so position graph becomes less steep and flattens out. velocity graph becomes negative, so position graph now has a decreasing value. It's going to have a negative slope. Velocity graph jumps back up to 0, so position graph has to flatten out. Velocity graph becomes positive, so the position graph has to have positive slope. So you can draw either one of these graphs from the other. And you'll be seeing examples of both cases. In fact, all three cases. Maybe you have the position graph and you want to draw velocity and acceleration. Or maybe you have the velocity graph and you want to draw position and acceleration. Or maybe you have the acceleration graph and you want to backtrack to velocity and position. Any questions on that so far? All right, then let's try using the velocity graph to draw the acceleration graph. As before, we want to split this graph into important instants in time. And since it looks like the velocity graph is all straight lines, or at least close to straight lines, all that really matters is where is the slope of those lines change. So if we consider, it looks like we have important changes at this instant when it changes from constant to decreasing. So that's going to be an important instant in time. This instant, when it changes from decreasing to constant again. We don't really care about it crossing 0 here because from here to here, the velocity changing from positive to negative, that's very important for the position graph because the position graph has changed from positive slope to negative slope. But the acceleration tells you the slope of the velocity. So we only, for drawing out the acceleration graph, we only care about where does the slope of velocity change. In this entire section, the slope is presumably a constant. So the acceleration is just going to be one value. Then from here to here, we've got just a flat line. From here to here, we've got a straight line. From here onwards, we've got a straight line. So we can now split up or figure out where the acceleration is going to be positive or negative based on the slope of the velocity graph. For instance, in this section, what's the slope of the velocity graph?
Zero.
Yeah, this whole section is 0 slope, and therefore it has to have 0 acceleration. What about in this section? What can you say about the slope?
It's negative and constant.
Right, we've got a negative constant slope. And then in this section,
It's 0 again.
Back to 0. And then in this section,
It's positive.
right, positive slope. And then it looks like we're back to 0 again. So that means the acceleration graph has to be 0 in these regions. In any region where the velocity is constant, the acceleration has to be 0 because constant velocity means no change in velocity, which means no acceleration. So we can fill those in right away. 0 acceleration during those periods of time. But then during these periods of time, the velocity decreasing rapidly means a very large negative acceleration. Velocity increasing rapidly means a large positive acceleration. So we're going to have negative acceleration in this region of time and positive acceleration in this region of time. And if these truly are straight lines, if we just got completely flat and then a sharp corner transitioning to a diagonal straight line, sharp corner transitioning to flat, and so on, then these would be instantaneous jumps. Because if this is truly changing from 0 slope to some negative slope, that means the acceleration instantly changes from 0 acceleration to a negative acceleration. However, that's not very realistic. Realistically, objects don't instantly change their velocity. It takes maybe a short but non-zero amount of time for that to take place. So realistically, it's not going to be a sudden drop. It's going to be a quick but not instantaneous change. So realistically, we should probably have some steep but not vertical diagonal lines connecting these. Because it does take a little bit of time to make that acceleration, to make the acceleration change. Because what causes an acceleration? You want an object to accelerate, what do you have to do? What causes acceleration to happen?
Change in speed.
That's what the acceleration is, but what do you have to do to make that happen?
Apply a force.
Right, you got to apply a force. Going back to Newton's second law, force equals mass times acceleration. In order for this object to accelerate in the negative direction, there has to be a force acting on it in the negative direction. And forces don't turn on and off instantly. Like if you've got an object and you want to apply a force to it, you can't just go from no force at all to all the force instantly. When you're in the process of applying that force, when you first make contact with the object, you're applying a little bit of force, then more and more and more. So it might be very quick if you're just slamming into the object. That might be very quickly changing from no force to lots of force, but it's not truly instantaneous. It does take some amount of time for that force to ramp up, to go from no force to lots of force. So realistically, every change in acceleration should take some amount of time. Mathematically, we sometimes treat it as an instantaneous change for simplicity, but that's just an approximation of what's actually a fast but non-instantaneous change. So mathematically speaking, that means that if we want to be truly realistic, these graphs should all be continuous. In fact, this is really where the idea of continuity in calculus comes from. The position graph being continuous means there's no teleportation. Velocity graph being continuous means there's no instantaneous changes in velocity. You can't just change from going at some speed to going at some other speed instantaneously. And the acceleration graph being continuous means forces take time to activate and deactivate. You can't just turn a force on and off instantly. It takes a little bit of time for that to happen. So realistically, all of these graphs should be continuous. But sometimes a sudden change is easier to analyze mathematically and is close enough to reality. Any questions on that so far? Also, a couple other things about this in terms of the derivatives. The velocity being the derivative of position, that means that since it's the first derivative, that tells you everything you need to know about the slope of the position graph. If the slope of the position graph is positive, greater than 0, that means x is increasing. If the position graph, or if the derivative is negative, that means x is decreasing. And if the velocity equals 0, what do you know is true about a graph if the derivative equals 0? What has to be true about a graph if its derivative is 0? It's constant. If it's 0 for a while. In fact, I should probably split this up. If the velocity is 0 for a while, then x is constant. Versus if the velocity is 0 for an instant. For example, right here, velocity has been 0 for an instant. That doesn't mean the velocity is constant or the position is constant. What does it mean though? If the derivative is 0 at that instant, what does that tell you about the function at that instant? What are you typically looking for in calculus if you set the derivative of a function equal to 0?
A max or min.
Exactly. You're looking for the max and min of the graph, if any. So if the velocity is constant for a while, that means, or sorry, if the velocity is 0 for a while, that means the position is constant. The object is not moving. But if the velocity has just tapped 0, if it's just passed through 0 on its way from positive to negative or from negative to positive, that's essentially a turnaround point. The object has come to a stop, but only for an instant. It's been like on its way in the forward direction, comes to a stop, and moves in the backwards direction. So at instants when the velocity is 0, when the velocity is changing from a negative value to positive or positive to negative, those are the turnaround points, when the position reaches a maximum value and turns around. Or maybe it's going backwards, reaches a minimum value and turns around. So if the velocity is 0 for an instant, that's x is a max or a min. And you could think of that as a turnaround point. The object has come to a stop. Like for instance, if you throw an object upwards, then there's an instant at the top of its flight where it's changing from positive velocity to 0 velocity to negative velocity. That's the turnaround point we're talking about here, where the position reaches its max. And so that's everything you can find from the first derivative. The first derivative tells you information about the function. And in the same way, velocity tells you information about the position graph because velocity is the first derivative of position. We can also get some similar information from acceleration, because acceleration is the first derivative of velocity, but velocity itself is the derivative of position. So acceleration is the derivative of the derivative of position. And what do we call the derivative of a function? If you take the derivative and then take the derivative again, what are you finding? Or what do we call that? Think of it in terms of notation. We got dd. How do you abbreviate dd? I mean, this isn't really multiplication, but if you treat it as multiplication, what's d times d?
D squared.
And dt times dt, if you just treat dt as one object?
Dt squared.
So d squared over dt squared, x, the second derivative of x. Acceleration is the first derivative of velocity, which is the second derivative of position, because velocity itself is the derivative of position. So the derivative of position is the second derivative of position. So everything you saw in calculus about second derivatives is true for acceleration. So if the acceleration is, and we can split this again into positives, negatives, and zeros. Acceleration is the second derivative of position. That might be positive, might be 0 for a while, might be 0 for an instant, or it might be negative. And do you remember what that tells you? From back in calculus, did you see what the second derivative tells you about the function itself? For instance, if the second derivative is positive, what does that tell you about the function? Well, let's compare those on these graphs. We've got a region where the acceleration is positive. In that region, what do you notice about the position graph in this region? Versus when the acceleration is negative, what's different about the position graph in that region? difference
Is that a
between,
minimum when the acceleration is positive?
what was that?
Does it have to do with the maximum and the minimums of the graph?
That is where the maximum and minimum occur. But notice that the acceleration isn't positive just at that instant. The acceleration is positive for this interval of time. So not just for the minimum, but for this entire portion. And what's the difference between that portion where the acceleration is positive or acceleration is negative versus where the acceleration is 0? In fact, let's start with that. We've got an entire region of time when the acceleration is 0. During that interval of time, what do you notice about the position graph? If the acceleration is 0 for a while, then the position graph is what sort of shape?
Linear?
Yeah, it's going to be linear. And conceptually, we can say no acceleration means no change in velocity. Velocity is constant. And constant velocity means the position has to be a linear function, because a linear function has no change in slope. So if the acceleration is 0 for a while, that means the position is linear. The graph of position is a straight line. And in terms of calculus, we can look at this in terms of a straight line is just going to be x equals slope times t plus intercept. X equals mt plus b. So that would be the equation of a straight line. If you take the derivative, we will get a formula for velocity. What's the derivative of mt plus b going to be with respect to t itself?
M?
Yeah, just m. Derivative of mt is just m. The slope derivative of plus a constant is 0. So if the position graph is a straight line, then the velocity will be a constant, which it is. And then if we take the derivative again, we get the acceleration. Well, what's the derivative of a constant?
0.
0. And these arrows work in both directions. If the position is linear, then the velocity is constant, then the acceleration is 0. But also in the other direction, if the acceleration is 0 for a while, not just at an instant, but for a while, if the acceleration is 0 for a while, then the velocity is constant during that period of time, and the position graph is a straight line during that period of time. So we know at least that if the acceleration is 0 for a while, then x is linear. Any questions on that so far? So try some more visual comparisons of what's going on when the acceleration is positive and what does the position look like, and what does the velocity look like as well. When the acceleration is negative, what does the velocity look like? What does the position look like during that period of time? Go back to any notes or textbooks you've got from calculus, see if you can find some information about what the second derivative tells you about a function. And also I've got a worksheet on derivatives that you might find very helpful here. Let me pull this up. Yeah, actually, let me just send the link there. If you go to math.ncheese.org/P7math, there's some math review worksheets. You want to specifically look at the calculus derivatives and calculus integrals. Take a look at those when you get a chance over the weekend, and I think that's going to be some very helpful review leading into these ideas of position velocity acceleration graphs. Because this really is just the graphs of a function, its first derivative, and its second derivative. We're just now attaching actual physical meaning to what those are. The function is position, the first derivative is the velocity, and the second derivative is acceleration. So take a look at those worksheets on derivatives and integrals, review anything you've got on derivatives and what they mean, specifically second derivatives as well from calculus. Feel free to email me if you have any questions on those, and you're welcome to bring those into any of the office hours or drop-in tutoring as well. Have a good weekend, and I will see you next time.